So I'm Kyle Brinkman. I'm a professor and the department chair in materials science and engineering here at Clemson. I've been at Clemson for 11 years now, and I'm going on my sixth year as department chair. I'm a Clemson alum. I graduated with a bachelor's degree in chemical engineering and a master's in materials science and engineering before graduate school in materials science and engineering at the EPFL in Switzerland. I joined Clemson after almost a decade in the Savannah River National Lab in the Department of Energy, where I worked on a wide range of material science and engineering challenges. So I work on ceramic-based materials. These are materials used in extreme environments, often at high temperature. We work on solid-state ionics for energy conversion and storage. These are materials that move ions through the solid-state material in order to affect electricity, like in batteries or fuel cells. And we also do some work on nuclear materials and some unique characterization aspects that involve the stability or the thermodynamic stability of materials. And what our group tries to do is pull all of these entities together to make new discoveries, either create new materials or put on protective coatings or structural modifications for materials to make them either perform longer or perform to a higher degree in terms of battery or fuel cell characteristics. My story, I did a undergraduate degree in chemical engineering, and I loved chemical engineering, and I loved my undergraduate program. But I found as I was a senior that I was really more interested in the fundamentals of the science and making or cooking materials in the lab than I was in an industrial setting or with scale up as a process engineer. My first experience with research was I did a National Science Foundation REU program when I was an undergrad. I spent a summer at the Sandia National Labs and University of New Mexico. And as part of that, I visited Los Alamos. Folks have seen the movie Oppenheimer. Just really, I was hooked. I was hooked on science. It was a great experience. Now, my research mentor at the time became the very next year a professor and faculty member here at Clemson. So as I finished my undergraduate, he convinced me to stay for a master's degree. So that was my entry into graduate school. After master's, I had to decide between jobs in industry or graduate school. And really, I wasn't ready to settle down. I wanted to explore some more, and I had opportunities. I chose to go to the Swiss Federal Institute of Technology in Switzerland, in Europe, and did a degree on ceramic thin films and semiconductors. I always knew I wanted to get into energy research, but I needed to find the way. I needed to find a way to kind of move into that area. And I think this is an interesting tale is how to do that. In my case, I wrote a proposal for a postdoctoral research fellowship that was awarded. It was in Japan. And with this, I had a host institution in Tokyo, and I had the ability to carve out my own research direction. And it's then that I intentionally started to move into energy materials and hydrogen. Later, when I served in the Department of Energy, I had experience with teams working on a wide range of materials, and that also really opened up my mind to different possibilities with materials research that I really otherwise would not have had. In terms of translation capacity, how to translate, university research to the marketplace. My view is, keep in mind what new product, service, or approach that you're creating that doesn't exist before. I think also creating and forming a company in the field opens up other possibilities for use-inspired research, SBIR and STTRs, that are otherwise conventionally not typically available in the standard NSF or DOE type grant. So I think it opens up new research possibilities while it also opens up possibilities to take research from the lab to marketplace. I think the biggest challenge with this is a couple. One is how to find the time. And in order to find the time, you have to decide really what's important enough to invest. So I think deciding on what's the important invention, concept that you're going to dedicate that time and energy to champion. And I think once that's decided, one can craft an approach that targets a specific market for that invention, while also being flexible and preserve the ability to tackle other opportunities as they arise. For example, in our current project funded by the South Carolina Research Authority, the overall concept was to take a patented design of a flat tube that has a really highly compact, unique design feature, taking into account three-dimensional printing of two different types of materials blended together. So it's a multi-materials processing and design concept, and it's ultimately aimed at solid oxide fuel cells for power in the near term. However, we have the opportunity to look at hydrogen production, and we also have, by the processing route, we have the ability to tackle challenges associated with 3D printing of ceramics and ceramic metal composites. And so I think keeping in mind a near-term objective, but also the broader perspective of how this technology can contribute in other fields, preserve some of that flexibility and ability to maneuver as the conditions change, as federal funding priorities change, as the market changes. For me, to identify the strategic direction and to get to the point to take the next step, personally, it was about establishing a track record and portfolio of really fundamental science discoveries, design aspects, and manufacturing type patents. So these are publications and patents that have taken place over really the last 20 years. Our patents in ceramic membranes, microstructure and processing. Some of those started in my time at Savannah River National Lab. Here at Clemson, we have patents on the materials, compositions themselves, on ceramic metal composites and compatibility in hydrogen, as well as different processing and 3D additive manufacturing techniques for ceramics. And at this point, let's say 5 to 6 patents that are directly applicable to this current technology. Each one of those is a multi-year effort. So I think by collecting these together, you're demonstrating your track record, your persistence in the field, and your ability to stay the course over periods of time. And I think that's important in a materials-based lab to market transition, which is capital intensive, time intensive, and simply takes time. You have to demonstrate that you have the ability and accomplishments to date in order to move that forward. Some of my most significant accomplishments in material science and engineering, I would say in early career stage, I had some Department of Energy early career awards, specifically in nuclear energy and Savannah River National Lab that really helped. At the mid-career stage, professional societies helped by some recognition in the American Ceramic Society, as well as the TMS Materials Society. At later stage, I'm now a fellow of 3 technical societies, the American Ceramics Society, the Royal Society of Chemistry, and also the World Academy of Ceramics, which names about 15 members a year. International Society, Clemson currently has 3 members of this prestigious society. In addition, I think the opportunity to lead technical divisions in these professional societies is really important. So it's both a service to the materials community, as well as some prestige to be able to lead that division which is a technical division focused on a certain research theme. To be able to lead the international community in a certain direction is a service, but it's also a privilege and it's great experience. I've served as an editor of an international peer-reviewed journal in material science. And I've had the privilege to serve as the department chair of material science and engineering here at Clemson, now going into my sixth year. And I've been on the executive committee of all of the material science chairs in the US for several years, sort of setting nationally the trajectory for material science and engineering. At Clemson, I've hired 8 out of our current 22 faculty and was involved in the conception, the design, groundbreaking, and now implementation of our new Advanced Materials Innovation Complex, which is a keynote for Clemson's future advanced materials initiatives as the only material science and engineering department in the state. Breakthroughs in material science and engineering related to nuclear. So nuclear energy, incredibly important. You know, the US gets approximately 20% of its power from nuclear. In addition to conventional reactors that are online, there's a so-called next generation of reactors. One of them involves a heat transfer medium, which is a molten salt. So we have some work on characterizing the structure of this molten salt and also its physical characteristics, its stability. The waste that's produced by both current generation of reactors and potential future types of reactors is something that has to be dealt with. So we have a number of projects dealing with how to incorporate the solid waste from potential commercial recycling scenarios to immobilize it into a solid matrix, and ultimately will go to a geologic repository. The baseline material for disposing of different nuclear waste, high-level waste from defense waste, is glass. And we've been considering a number of alternatives, such as crystalline ceramic materials that mimic nature. So the idea is to go into a rock formation and extract a mineral that's been around for 100 million years. And now, in order to target a really stable waste form, we would intentionally try to synthesize that rock formation in the lab with the radioisotopes of concern. And the fact that that rock or mineral has been around for geologic timescales gives us as a society confidence that the material we make as a waste form will have long-term durability and stability. There's also off-gas capture. So as you reprocess nuclear waste, if that was a direction that the US would take, which would be potential recycling of used fuel, one would reprocess it. And in that process, there would be some volatile species that would be released. And we have some work on our membrane materials and new generation of materials to capture species such as iodine or hydrogen and hydrogen isotopes. And many of these materials that we would use to capture hydrogen isotopes, for instance, are materials that we've investigated in our solid oxide fuel cell work. So there's a dual use and perspective that we bring. How to take materials in one system and use them in another application area. There's also nuclear fusion, and these are work that we're doing on materials for handling and processing hydrogen and hydrogen isotopes in collaboration with colleagues in the Battelle Savannah River Alliance at Savannah River National Lab. Difficult decisions in research. I think the first step is to define what is your problem, an area that you're working on. And so the first step is defining the problem, and try in the solution to go in a different or a new direction. Don't go down the path that everyone else is taking. I think one of the thought processes is what are my unique capabilities and insight and that I bring to the table, and how is this a different approach? I think often that thinking process comes from getting into new areas. And I think that's something that a lot of folks are afraid of. I mentioned my work in Department of Energy, Savannah River National Lab, where I was on big group teams, maybe working on a project with a cryptographer and a mechanical engineer and a chemical engineer and all different types of backgrounds coming together to solve a problem, is you often come up with very unique solutions that you would have not otherwise had. And the other tangent to that is don't be afraid to get into new areas. Some of our insights into new materials for batteries or fuel cells have come from our work on nuclear materials. So when, for example, when we were trying to design a stable mineral system that would be able to lock up or trap a radionuclide in a very stable form, we learned a lot about how to make and design a crystal structure to do that. Well, if we tweak that crystal structure so that now that species is no longer trapped, but is now mobile to move throughout the structure, we can now design a better battery or ion conductor that can be used in a fuel cell. And so I think taking the approach of, what is the road less traveled? What are the opportunities? Where's the avenue that I have the biggest opportunity to contribute based on my unique capabilities, my background, and then to take it in general in a direction that folks are not looking in. My advice to researchers looking to translate research into practical applications is to consider the three whys. Why you, why now, and why this specific technology? So I think things have to align. It can't be about you. It can't just be about the specific technology. There has to be a timing, right? There has to be a market need, a societal need, and you, the technology, and the timing has to come together and be aligned in order to really be successful in translating the lab market into practical research applications.